Welcome to the problem walkthrough for LeetCode number 1563, Stone Game V. In this session, we'll explore a challenging dynamic programming problem that involves strategic thinking and recursive calculations. Let's dive into the problem, break it down, and uncover an optimal solution. In this problem, Alice and Bob are playing a game called Stone Game V. The game starts with a single pile of stones represented by an array of integers called stone value. Each element in this array corresponds to the value of a specific pile of stones. Alice and Bob take turns to play, with Alice going first. On each turn, the player must split the current pile into two non-empty contiguous subarrays. After the split, the player earns points equal to the sum of the values in the smaller subarray. If the two subarrays have the same sum, the player can choose either one to earn points. The game proceeds until there is only one stone in each pile. The goal for both players is to maximize their total points, and your task is to determine the maximum number of points Alice can earn if both players play optimally. The output of the problem is a single integer representing the maximum points Alice can earn. Let's look at an example. Suppose stone value is 6, 2, 3, 4, 5, 5. In the first turn, Alice splits the array into 6, 2, 3, and 4, 5, 5. The sum of the smaller subarray is 11, so Alice earns 11 points. On Bob's turn, he splits 6, 2, 3 into 6 and 2, 3. The sum of the smaller subarray is 6, so Bob earns 6 points. Next, Alice splits 4, 5, 5 into 4 and 5, 5. The sum of the smaller subarray is 9, so Alice earns 9 additional points. Adding her points together, Alice's total score becomes 11 plus 9, which equals 18. Now consider another example where stone value is 7, 7, 7, 7, 7, 7, 7. In this case, since all elements are equal, the splits result in subarrays with equal sums. Both players continue to split optimally, and Alice earns a total of 28 points. Finally, let's look at an edge case where stone value is 4. Here, Alice cannot make any move because the array contains only one element. Since no splits are possible, Alice's score is 0. This example highlights the importance of handling edge cases where the array size is minimal. The constraints ensure that the array length is at least 1 and at most 500, with each element having a value between 1 and 10,000. To solve this problem efficiently, we can use dynamic programming techniques. By pre-computing prefix sums, we can simplify the calculation of subarray sums, and memoization helps optimize the recursive solution. Key edge cases to consider include arrays with only one element, where no splits are possible, arrays with equal elements, where players can choose either subarray in the case of ties, and arrays with alternating large and small values, where players need to carefully choose splits to maximize their scores. The optimal solution has a time complexity of approximately O(n cubed), making it feasible within the problem's constraints. To solve the Stone Game V problem, we need to consider how to approach splitting the array into two non-empty parts and calculating scores based on their sums. A natural first thought is a brute force approach. Here, we explore all possible ways to split the array recursively. For each split, we calculate the sums of the left and right parts, choose the part with the smaller sum or both if the sums are equal, and then repeat the process recursively. While this method is straightforward, the computational cost is extremely high. Since we explore all splits for every subarray, the time complexity grows exponentially, approximately O(2 to the power of n). This makes it impractical for larger inputs, where n exceeds 20, as the number of computations becomes astronomically large. Clearly, we need a more efficient method to handle larger constraints. To address the inefficiencies of the brute force approach, we turn to dynamic programming with memoization. The problem can be broken into overlapping subproblems, which makes it suitable for DP. We define a 2D DP table, where dp, I, j, represents the maximum score obtainable for the subarray from index I to j. To speed up calculations, we pre-compute prefix sums, which allow us to quickly calculate the sum of any subarray in constant time. For each subarray, we try all possible split points and use the prefix sums to compute the sums of the left and right parts. Based on these sums, we calculate the scores for the left or right part, or both if the sums are equal, and combine them. These results are stored in the DP table to avoid redundant computation. The time complexity of this approach is O(n cubed, which is significantly better than the brute force method, though it can still be slow for very large inputs. The space complexity is O(n squared, which is manageable for most constraints. A further improvement is to optimize space usage by replacing the 2D DP table with a rolling 1D array. This reduces the space complexity to O(n), but the time complexity remains cubic, meaning it's still a challenge for extremely large inputs. Ultimately, we chose the dynamic programming approach with a 2D DP table as our solution. The key insight is that the problem can be broken into smaller overlapping subproblems, making it a natural fit for DP. Pre-computing prefix sums allows us to efficiently calculate subarray sums, saving significant time during computation. Memoization ensures that each subproblem is solved only once, avoiding redundant work. We opted for the standard DP approach over the space-optimized version because the additional clarity and simplicity of using a 2D table outweigh the marginal benefits of reduced memory usage. The brute force method, while conceptually simple, is impractical due to its exponential complexity. Meanwhile, the space-optimized DP approach does not improve runtime and offers limited advantages for the given constraints. Overall, the 2D DP approach strikes the right balance between runtime efficiency, memory usage, and clarity, making it the most suitable choice for inputs up to n equals 500. In this problem, we're tasked with splitting an array into two non-empty subarrays multiple times and calculating a score based on the sums of the elements in the left and right subarrays. The ultimate goal is to determine the maximum possible score we can achieve after exploring all valid splits. To break it down, the input is an array of integers, and each split occurs at an index I, where the array is divided into a left subarray containing elements from the start to index I1, and a right subarray containing elements from index I to the end. The score for each split is derived from a specific formula involving the sums of these two subarrays. To solve the problem, we need to systematically consider every possible split, compute the scores, and identify the maximum score achievable. To begin, we can consider a straightforward brute force approach. First, we loop through all possible split points, iterating over indices from 1 to n1. At each index, we divide the array into two parts, the left subarray and the right subarray. Next, we calculate the sum of elements in both subarrays, which will allow us to compute the score for that particular split using the given formula. As we process each split, we keep track of the highest score encountered so far by maintaining a variable called max_score. After iterating through all possible splits, we return this max_score as the result. However, this method is inefficient because calculating the sums for each split requires O(n) time, and with n1 splits to process, the overall time complexity becomes O(n squared). Additionally, this approach recalculates subarray sums from scratch for each split, which introduces redundant computations and leaves room for optimization. To address the inefficiencies of the brute force approach, we can use prefix sums, a powerful data structure that allows us to compute subarray sums in constant time. The idea is to create a prefix sum array where each element at index I stores the cumulative sum of elements from the start of the array up to index I1. With this array, the sum of the left subarray for a split at index I becomes prefix I, and the sum of the right subarray becomes prefix I, where prefix n represents the total sum of the array. This eliminates the need to recompute subarray sums repeatedly. To set this up, we first initialize a prefix sum array of size n+1 with all values set to 0. Then, we compute the cumulative sums by iterating through the input array. This pre-processing step has a time complexity of O(n), making it highly efficient. Once the prefix sum array is ready, we can iterate through all possible split points and compute the scores efficiently. For each valid split point, we calculate the sums of the left and right subarrays using the prefix sum array. Specifically, the left sum is obtained as prefix I, and the right sum as prefix I. Using these sums, we calculate the score for the split based on the provided formula. We then compare this score with the current maximum score stored in the variable max_score, updating max_score if the new score is higher. After processing all split points, we return max_score as the result. This optimized approach benefits significantly from the prefix sum array, as it avoids recalculating subarray sums for each split, reducing the overall time complexity from O(n) squared to O(n). Finally, we need to consider several edge cases to ensure the algorithm handles all scenarios effectively. For instance, if the array contains only 2 elements, there is only one valid split to evaluate. When the array includes negative numbers, the algorithm must correctly handle these values when computing sums and scores. Additionally, if all elements in the array are identical, the scores for all splits will be the same, and the algorithm should account for this. In terms of complexity analysis, the time complexity of the optimized solution is O(n), with O(n) for computing the prefix sum array and another O(n) for iterating through the splits. The space complexity is also O(n), as we store the prefix sum array. This makes our approach both time and space efficient for solving the problem. Here, we start by defining the StoneGameV method within the solution class. The first thing we do is calculate the length of the stone value array, which represents the values of the stones. To make range sum calculations more efficient, we pre-compute prefix sums. This is stored in the prefix_sums array, where each element represents the cumulative sum of the stones up to that point. Using this, we can efficiently calculate the sum of any subarray by subtracting 2 prefix sums. Next, we define a helper function called range_sum. This function takes 2 indices, left and right, and returns the sum of the subarray between these indices using the pre-computed prefix_sums. This avoids recalculating the sum from scratch multiple times, which improves the performance significantly. We then initialize a 2D list DP to store the maximum score Alice can achieve for any subarray. The dimensions of DP are n x n, where n is the length of the stone value array, and it is filled with zeros initially. Each cell DP, left, right, will eventually represent the maximum score Alice can achieve when considering the subarray from index left to right. Now, we iterate over all possible lengths of subarrays, starting from 2 up to the total length of the array. For each length, we determine all possible starting points, represented by left, and calculate the corresponding ending point, represented by right. For each subarray, we explore all possible split points k between left and right. At each split point, we calculate the sum of the left and right subarrays using the range_sum function. If the sum of the left subarray is less than the right subarray, we update DP, left, right, with the maximum score Alice can achieve when she chooses the left subarray, adding the current score to the value stored in DP, left, k. If the sum of the left subarray is greater than the right subarray, we instead update DP, left, right, with the maximum score Alice can achieve by choosing the right subarray. In this case, we add the right subarray's sum to the value stored in DP, k plus 1, right, which represents the score Alice can achieve from the right portion of the array after the split. Now, if the sums of the left and right subarrays are equal, Alice can choose either subarray. Here, we calculate the maximum score Alice can achieve by considering both options. We take the maximum of 3 values, the current value of DP, left, right, the score obtained by choosing the left subarray, and the score obtained by choosing the right subarray. This ensures Alice always makes the optimal choice for maximizing her total score. Finally, after iterating over all possible subarrays and split points, the solution to the problem is stored in DP, 0, and 1. This represents the maximum score Alice can achieve for the entire array, starting from the first stone to the last stone. We return this value as the result of the StoneGameV method. Here, we start by importing the necessary packages and defining our solution class. The main method, StoneGameV, takes an array stone value as input, representing the values of the stones. The first step is to calculate prefix sums, which will allow us to efficiently compute the sum of any subarray. This is achieved by iterating through the stone value array and maintaining a cumulative sum in the prefix sums array. Next, we define a 2D array DP, which will serve as our memoization table. Each DP, I, j, will store the maximum score the current player can achieve for the subarray starting at index I and ending at index j. We then iterate over all possible lengths of subarrays, starting from 2 and going up to the length of the stone value array. For each subarray, we determine the left and right bounds and explore all possible ways to split the subarray at different points. By considering each split point, we calculate the sum of the left and right segments using a helper function, rangesum, which utilizes the prefix sums for efficiency. If the sum of the left segment is smaller than the right, we update DP, left, right, to include the left segment's sum along with the optimal result from the left subproblem. If the left segment's sum is greater than the right, we instead add the right segment's sum along with the optimal result from the right subproblem. However, if the two segment sums are equal, we have to consider both possibilities, adding either the left or the right segment's sum along with their respective subproblem results. In this case, we take the maximum of the two outcomes to ensure the best score. After iterating through all split points for the given subarray, the DP table stores the optimal result for that subarray. Finally, the method returns DP, 0, and 1, which represents the maximum score the first player can achieve for the entire array. Additionally, the range_sum helper function is defined to efficiently compute the sum of a subarray using the prefix sums array. It simply subtracts the prefix sum at the start index from the prefix sum at the end index, ensuring that range sums are calculated in constant time. This approach ensures that the solution is both optimal and efficient, leveraging dynamic programming and prefix sums to solve the problem effectively. To solve the problem, we start by examining the first example with the input array 6, 2, 3, 4, 5. First, we initialize some essential variables. The length of the array, n, is 5. We compute the prefix sums, which will help us calculate the sum of any subarray efficiently. The prefix sums for this input are 0, 6, 8, 11, 15, 20. Additionally, we set up a memoization table DP, a 5x5 matrix initialized with zeros, to store the maximum scores for subarrays. Then, we process subarrays of increasing lengths, starting from 2. For subarrays of length 2, take 6, 2, with indices 0 to 1. Splitting at k equals 0, we calculate the left sum as 6 and the right sum as 2. Since the left sum is greater than the right sum, we update DP 0, 1 to 2, which is the right sum plus the best score from the right subarray. Similarly, for the subarray 2, 3, with indices 1 to 2, splitting at k equals 1 gives us a left sum of 2 and a right sum of 3. Here, the left sum is smaller, so the score update rule considers the left subarray, and DP 1, 2 becomes 2. This process continues for all subarrays of length 2. Next, we move to subarrays of length 3, such as 6, 2, 3, with indices 0 to 2. We consider splits at k equals 0 and k equals 1. Splitting at k equals 0, the left sum is 6 and the right sum is 5. Since the left sum is larger, we update DP 0, 2 to 7, which is the right sum plus the best score from the right subarray. Splitting at k equals 1, the left sum becomes 8 while the right sum is 3. Again, the left sum is greater, but no additional update is made to DP 0, 2, as the score remains the same. Continuing this process for other subarrays of length 3, we compute and update the DP table. The process repeats for longer subarrays, up to the full array length. Ultimately, the maximum score for the full array is stored in DP 0, 4. For this example input, the value of DP 0, 4 is 18, which is the final output. In our second example, the input is 1, 1, 1, 1, 1. We follow the same initialization steps. The length of the array, n, is 5, and the prefix sums are 0, 1, 2, 3, 4, 5. The DP table is again a 5x5 matrix initialized with zeros. Starting with subarrays of length 2, consider 1, 1, with indices 0 to 1. Splitting at k equals 0, the left sum is 1 and the right sum is also 1. Since the left and right sums are equal, we update DP 0, 1 to the maximum of 1 plus DP 0, 0, and 1 plus DP 1, 1, which results in 1. This calculation is repeated for all subarrays of length 2, updating the DP table accordingly. For subarrays of length 3, consider 1, 1, 1, with indices 0 to 2. Splitting at k equals 0, the left sum is 1 and the right sum is 2. Since the left sum is smaller, we update DP 0, 2 to the maximum of the left sum plus the best score from the left subarray, which results in 1. Splitting at k equals 1, the left sum becomes 2 and the right sum is 1. Here, the left sum is larger, but no change is made to DP 0, 2, as the score remains the same. This process is repeated for all subarrays of length 3 and longer. Ultimately, the maximum score for the full array is stored in DP 0, 4. For this example, the final output is 4. In the third example, the input is 7, 7, 7, 7. The initialization steps remain the same. The length of the array, n, is 4, and the prefix sums are 0, 7, 14, 21, 28. The DP table is a 4x4 matrix initialized with zeros. Starting with subarrays of length 2, consider 7, 7, with indices 0 to 1. Splitting at k equals 0, the left sum is 7 and the right sum is also 7. Since the left and right sums are equal, we update dp 0, 1 to the maximum of 7 plus dp 0, 0, and 7 plus dp 1, 1, which results in 7. This calculation is repeated for all subarrays of length 2, updating the dp table. For subarrays of length 3, such as 7, 7, 7, with indices 0 to 2, we consider splits at k equals 0 and k equals 1. Splitting at k equals 0, the left sum is 7 and the right sum is 14. Since the left sum is smaller, we update dp 0, 2, following the rule for smaller left sums. This process continues for all subarrays of length 3 and longer. Finally, the maximum score for the full array is stored in dp 0, 3. For this example, the result is 21, which is the final output. To analyze the time complexity of our solution, we start with the prefix sum calculation. The prefix sum array is constructed by iterating through the stone value array once, making this step O, n. Next, we initialize a dynamic programming table, dp, which is a 2D array of size nxn. Since we must allocate and set up this table, the time complexity for initialization is O, n squared. Now, we move to the main computation. For different subarray lengths, we iterate over all possible lengths from 2 to n. This means the outer loop in our implementation runs approximately n1 times. For each subarray length, we then calculate all possible subarrays by iterating over their starting points. The starting point, left, ranges from 0 to n length, and this gives O, n, iterations for each fixed length. Together, these steps lay the foundation for the overall complexity analysis. Now, let's consider the split points within each subarray. For any subarray defined by left and right, we evaluate all possible split points k between left and right 1. The number of split points depends on the subarray length, which means there are O, length, splits to evaluate for each subarray. Combining this, for each subarray length, the total operations amount to approximately O, n, subarrays multiplied by O, length, splits, giving O, n asterisk length. If we sum this over all lengths from 2 to n, we get a total of O, n asterisk 2, plus O, n asterisk 3, plus O, n asterisk n. This simplifies to O, n asterisk, 2 plus 3 plus n, which evaluates to O, n asterisk, n squared, slash 2. This ultimately gives us a time complexity of O, n cubed. Additionally, range sum calculations are highly efficient at O, 1, per query, thanks to the prefix sum array. Therefore, the overall time complexity of the solution is O, n cubed. Next, we analyze the space complexity of the algorithm. First, the prefix sum array, prefix underscore sums, which is used for efficient range sum queries, is of size n plus 1. This requires O, n, space. The main component of our space usage is the dynamic programming table, dp, which is a 2D array of size nxn. This table stores the computed results for overlapping subproblems and requires O, n squared, space. Lastly, the algorithm uses only a small amount of auxiliary space for loop variables and function calls, which amounts to O, 1. Combining these components, the total space complexity of our solution is dominated by the dp table, making it O, n squared. Let's compare this optimized approach to a brute force solution. A naive method would involve recursively evaluating every possible split point for every subarray without any memoization. This approach leads to redundant computations, significantly increasing the number of subproblems. Specifically, for each subarray, we would evaluate O, n, splits. For a subarray of size n, there are O, 2 to the power of n, possible ways to split it. As a result, the time complexity of the brute force solution grows exponentially, approximately O, 2 to the power of n. In contrast, the dynamic programming approach avoids redundant calculations by storing results for overlapping subproblems. This reduces the time complexity to O, n cubed, making it far more efficient for larger input sizes. Finally, let's examine the best, average, and worst-case scenarios for this algorithm. In all cases, the algorithm processes the same number of subarrays and split points, as these depend solely on the input size and not on specific values in the array. Therefore, the time complexity remains O(n) cubed across the best, average, and worst cases. To mathematically validate the O(n) cubed complexity, consider that the algorithm uses nested loops, one iterating over subarray lengths, another over starting indices, and a third over split points. Each loop contributes a factor of O(n), resulting in O(n) equals O(n) cubed. Range sum queries are O(1) due to the prefix sum array, so they do not change the overall complexity. Thus, the cubic time complexity of O(n) cubed and the space complexity of O(n) squared are consistent across all scenarios, with the DP table being the dominant factor in both cases. When working on Stone Game V, there are several common pitfalls to watch out for. First, it's easy to overlook edge cases, especially when the array has very few elements like 2 or 3. Even though the problem specifies non-empty parts, your solution must ensure the splitting logic handles these minimal cases correctly. Another frequent mistake is implementing incorrect partitioning logic. If your loop doesn't properly divide the array into 2 non-overlapping parts, it can lead to duplicate calculations or invalid splits, which will compromise your results. Inefficient sum calculations are another issue. Directly recomputing sums for every split in a brute force approach can quickly escalate the time complexity to something like O(n) squared. Instead, consider using prefix sums to compute subarray sums much more efficiently. Additionally, be mindful of integer overflow, especially in languages like Java or C++ where large sums can exceed the range of an int. Using data types like long or implementing techniques to prevent overflow is essential. Lastly, many solutions fail to optimize for repeated calculations, such as recalculating the same subarray sum multiple times. This can be mitigated effectively with memoization or dynamic programming to save intermediate results for reuse. Now, let's talk about insights that are particularly useful in interviews. One key takeaway for problems involving divide and conquer or partitioning is the importance of prefix sums or cumulative arrays. These tools help reduce redundancy, making solutions more efficient. Recognizing patterns is also critical. For instance, many problems that involve splitting arrays require balancing computational overhead and memory usage. For example, prefix sum arrays use additional space but save time on recalculations, while recalculating sums might save space but increase computation. It's beneficial to start with a brute force approach to understand the structure of the problem, but you should actively search for optimizations to improve time complexity. Interviewers highly value seeing this thought process. Additionally, always clarify boundary constraints with the interviewer, like the array size or the range of allowed values. This ensures your solution is robust and accounts for edge cases. Similar problems worth exploring include LeetCode 53, which focuses on maximum subarray sums, and LeetCode 560, which demonstrates the power of prefix sums for counting subarray sums. Other related problems include LeetCode 124, which uses divide and conquer for binary trees, and LeetCode 1014, which involves pair-based optimizations. Finally, let's explore some alternative approaches to solving this problem. One effective technique is prefix sum optimization. Here, you pre-compute a prefix sum array, where each element represents the cumulative sum up to that index. This allows you to calculate subarray sums in O(1) time during the main logic. The trade-off is that it requires additional O(n) space to store the prefix sums, but the reduction in redundant calculations can be significant. Another approach is dynamic programming, where you use a DP table to store intermediate results, such as the best scores for specific partitions. This method is highly efficient but requires careful attention to indexing, which can make it challenging to implement quickly during an interview. Lastly, there's the sliding window technique, which is useful in scenarios with fixed-size subarrays or specific rules about subarray sizes. It allows you to calculate sums efficiently while iterating through the array. However, this approach is only applicable when the problem constraints align with fixed-size partitions, so it's not always universally applicable. Each of these methods has its own strengths and trade-offs, and understanding when to use them is key to mastering problems like this one. Great job! To wrap up, we reviewed the problem, summarized the solution, and highlighted key learnings. Remember, practicing problems like this will sharpen your dynamic programming skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!